A very good evening to one and all, and it's a great pleasure to be speaking for AIMS Rishikesh today. What I've tried to do is I've tried to put in some basics about AI and ML, about some techniques, and then about the specific topic that is about the feature selection and classification for COVID data. Talking about today's agenda, we'll talk about some introductory concepts, some basics about techniques, and then specific use case to healthcare, which is what we are going to discuss. So if we talk about actually AI, so we have a broader field which is called cognitive science. So AI actually is a part of cognitive science, and as we all know that cognitive science basically deals with the understanding of the mind, how nervous system represents processes and transforms information and all that stuff. So AI is actually part of it, and there are many other fields. So cognitive science in itself is a multidisciplinary area. Talking about AI, so what does actually AI mean? So of course, as the English word artificial means something which has not been naturally occurring but has been created by explicit efforts, humanly efforts. And intelligence, of course, means the capability to understand and acquire knowledge. And AI put together would be computer systems which try to emulate human brains or human intelligence. Now, AI in itself is a multidisciplinary area. So it derives upon lots of fields like computer science, neuroscience, biology, mathematics, probability and statistics, philosophy, and so on and so forth. And it's very difficult to say that this is AI and this is not AI. Now, often, many a times, there is some kind of confusion between the relationship between AI, ML, and DL. So artificial intelligence is actually a superset comprising of subsets like machine learning, and then a subset is a deep learning. So basically, when we are talking about generally about machines trying to emulate human intelligence, we call it artificial intelligence. In machine learning, we try to talk about algorithms and methods and approaches that are based upon learning. So when I talk about learning, that is making the machines to learn or computer systems to learn some data and to be able to gather some inferences from it. And then when we talk about deep learning, we are specifically talking about those AI techniques that use neurons that are inspired by human neurons and the similar concepts. So we'll talk about some of the introductory terms so that we can understand the other things. So now it's very important to understand machine learning and AI. So basically, when we talk about machine learning, we are talking about generating how we are going to predict or how we are going to actually generate some facts, given that we have some data which we can call historical or old data, that is data about events that have occurred. This includes medical events. And then there can be new concepts. So concepts can also keep on evolving. So we should be able to also generate information about evolving concepts. For example, COVID was never talked about till it actually arrived. It was somewhere, the term was there, but it wasn't much talked about. So then this is a new concept which came in at that time when the pandemic hit us. Similarly, how do we actually, distinguish different situations and newly generated situations and all that? And then we want the machines to learn all this so that they become intelligent to be able to predict something which we want them to predict. So talking about major AI techniques, so we have supervised learning, unsupervised learning, regression. I'll be talking briefly about each of these as we go along. And when we talk about supervised learning, deep learning is also part of supervised learning. So if we talk about supervised learning, whenever we talk about supervised learning, we are actually talking about classification. And classification goes along with prediction. So in this particular case, when we talk about classification, as the English word classify, means that we want to group the data. Here in this particular case, when we talk about classification, we actually are having, we deal with building of a model. Now, what this model means, it's just a function. For example, y is a function of x, where x can be some input variables. We can also call them attributes, or x could be some inputs, or x could be some medical parameters that are of importance, and y would be the class label that is derived by applying function f on x. So I'll repeat that y is a function of x, and the job of classification is to be able to find out y correctly, where y is nothing but the class label, and x is the set of inputs which we give to this process, and the process of finding the model, the classifier model, is to find out the correct function f. Right. Now, the function f could be anything. It could be linear, it could be non-linear. Like, for example, y could be as simple as y is equal to mx plus c, which we used to study in class 8th or 10th or something. Or it could be some complicated non-linear function. And there are different ways to model the data. And when we try to find out the function f, our primary task is to be able to find out the label y on the data correctly. Now, what is label? Labels are nothing but group identifiers. For example, in medical terms, we could have a diseased individual and a healthy individual. So our class labels would be healthy and diseased. So the categories that are available in the data are nothing but the class labels. In the process of classification, we should also always have something called the training data set. Training data set is a special data set because it contains the values of the input variables and the class labels. And we use it to build the model. And then after building the model, we are going to use the model to predict the class label. And we will actually compare the predicted class label and the given class labels and see how much of match is there. If the match is within the threshold we want it to be, say there's a 90% match or there's a 80% and 80% is good enough for us, then we say that our classifier is ready. Of course, there are some other parameters, but I'm generally talking about what modeling means. Now, this means that it's very, very important to actually have the training data set. Training data set must be complete. That is, it should contain all the use cases that the classifier is supposed to predict in future. Okay. Very crudely speaking, we can call the classifier, uh, you know, um I can say very crudely, just like a talking parrot. You make it learn some information like question and answers kind of thing. I mean, I would not say the classifier is so much organized, but you make it learn the data, and whatever it has learned, only it will reproduce. The moment it encounters something which it has not learned, it will fail. And therefore, it's very important for the classifier to be built on a training data set which is complete in the sense that it includes all the use cases which it is supposed to predict. Of course, the irony is that you always cannot predict. I mean, you always may not have the data which you may, for which you may require prediction in future. But of course, there are other ways to mitigate this problem. So presently, I'll not talk about this for sake of time. I'll take the questions at the end. I can see something on the chat. So then there are a lot of applications of classification in the medical domain. As you all already know, we have, the classification of various kinds of diseases, the causes. Then we can use this for image analysis and classify the image to be diseased or to be of a normal person. It can also help in drug discovery and classifying the drugs and so on and so forth. So then, quickly going over the next important set of techniques which fall in the category of unsupervised learning. By the way, supervised learning is called supervised learning because we do have the class labels in advance. That is, in the training data set, we have the class labels given to us. And once the model is built using the training data, then we use it to predict the class label for records which are unseen. So unseen records are those for which we don't have the class label and we use the classifier to predict them. Now talking about clustering. Clustering, verbatim is very similar. It is also grouping, but it is unsupervised learning process. It's called unsupervised because we do not have the class information in advance. Right. So what we are going to do is we are going to group the data in this case, and we the grouping will be done on some notion of similarity, and the notion of the similarity must be correctly identified. For example, if we want to cluster people on the basis of their traits of having hypertension, then we cannot, just cluster them on some basis which is not going to help us find out clusters that we want. Say we, cluster them on the basis of just female males or something like that, until unless there's a correlation. So to be able to cluster, we must be able to find out the notion of similarity that we should correctly use, and also we need a measure which is going to help us quantify the similarity between the data so that we can cluster it, right? So now just if we were to visualize clusters, this is just a 3D data space, and we want to, in the process of clustering, we want to minimize the cluster distances within the cluster, that is the intra cluster distances, and we want to maximize the inter-cluster distances, that is the distances across the clusters. Again, clustering has a lot of applications in medical domain. We want to cluster the population given to us on the basis of different diseases or symptoms, and so on and so forth. We can, use it for segmentation of patients, and so on and so forth, and so on and so forth. Right. So I can see some questions. I'll take them towards the end once I'm done. So we'll come back. Then talking about regression. So regression usually is used, very popularly in predictive analytics and in forecasting. So for example, I want to forecast the inflow of patient given a particular month and a day, or given a week, or if I want to forecast some, disease trends, or I want to forecast some symptoms. So wherever forecasting is required, regression is what we use. There are other use cases of regression also in, in the medical domain. For example, we may want to fill in missing values using regression, and so on and so forth. Then talking about anomaly detection. What is an anomaly? So anything which is very different from normal is said to be anomaly. In the medical domain, anomalies of utmost importance, because anomalies are, what the medical practitioners look for. And different kinds of supervised, unsupervised techniques, as well as statistical methods, can help identify anomalies. Uh, right. So now I just very broadly talked about some of the techniques that I use. Now let's go to the specific portion on which is the one that we wanted to discuss today. So this is a research paper that has been accepted and will be published in the IEEE Big Data 2023, which is to be held in this month in Sorrento, Italy. And it talks about ensemble-based feature identification and classification for COVID health record data. So, of course, we all know the importance of the pandemic and how COVID affected the lives of people. This study was done with patients from Mexico, with the data collected from patients, COVID patients from Mexico, and it amounted to around 10,48,576 patients with 21 attributes that were collected from them. The attributes that were collected are shown here. Some of the important ones are, the intubed, that is whether they received intubation or not, they suffered from pneumonia or not, they had COPD, hypertension, or they were suffering from some immunosuppressant diseases, or they were having asthma, and so on and so forth. So these were some of the important attributes that were available on the data. Some of the attributes were binary in nature. When I say binary, means they were having only two values. For example, of course, sex would be male and female, or it would be pregnant, yes or no. It would be intubed, yes or no, or COPD, yes or no, and so on and so forth. So there were two kinds of variables, one which were numeric, that is they had values, and the other which were Boolean, which had two values, only two values in them. What we did was that the class labels that were given in the data were primarily of three categories. One, that was zero, that is patient which had symptoms but were actually found as COVID negative. Then that was category zero. Then there was category of class one, label one, which were patients had symptoms and they actually suffered from COVID, but they survived. And class label 2, which meant that patients that had symptoms, they were COVID positive and could not survive. And we can see the breakup. So the class 2 was the least, that is 52,138 records were of that kind. So now we try to, use different methods to be able to classify. So the objective here is to develop a classification model which will be able to predict, given these input variables, which I had shown the 21 attributes. If we are having these 21 attribute values, then we should be able to predict in future that whether there is a possibility of such a patient, if he's suffering from COVID, should the patient would survive or he would not be able to survive. That was the objective of the study. We tried to classify, and we found out that when we used any particular single type of classifier, then the accuracy was not coming out good. So we actually worked on an ensemble model where we tried to choose multiple classifiers and stack them to finally build a hybrid classifier with increased accuracy and other precision recall and other parameters that are of importance. So we did multiple iterations over the different attributes, and we also try to find out the importance of different attributes, as you are seeing in these graphs. That for the different iterations, we were able to find out the importance of different attributes, and we could find out that the top n number of attributes were common across all the iterations. For example, having COPD, having obesity, diabetes, and so on and so forth. And then finally, we try to compare our work with the other baseline models for the various performance metrics such as precision, recall, F1 score, and accuracy. And as you can see that our method, which is the one in the lowermost row out here, gave the best performance. And we also try to, compare this with other classifiers, random forest, XGBoost, AdaBoost, and so on and so forth. We have also used deep learning techniques, which are not shown part of this particular slide deck. We also try to find out the AUC ROC curve. And you can see that the more the area that is covered under the curve, as you can see by the green cover, the better the performance of the classifier is. And for our proposed method, you can see that the green curve covers the maximum area, and therefore its performance was coming out to be the best. Specifically for class 2, which is refers to those particular patients that had COVID and were not able to survive. So we are able to actually predict the survival versus non-survival in a very good way. So I think there was also some exploratory analysis, but for sake of time, I will just skip all these and just conclude here. And I'll open for questions.